I'm Kevin Romano. I'm on the incident response team here at Arista, formerly on the managed network protection and response team about a year. So I bring some real world cases where we detected active compromise and some other use cases where we can help threat hunt and also do some retroactive search. So the first story I want to talk about is kind of beating an endpoint detection response to detection of a compromise. We have a managed network detection response customer running our Arista AVA security platform. And on our team, we bring in alerts from the system. So we're triaging alerts and we're doing some event reduction for the customer, but we're also doing proactive hunting where we're searching for, in this case, it was looking for domains created in the last year and that are new to the environment. So as a threat campaign may gear up for their next attack, they're going to bring up all new infrastructure, maybe get some domains created, things that aren't already on indicator of compromised lists out in the threat intelligence community, and then they'll launch that attack. So we look for those things, anything that's new and newly created domains, and maybe uncategorized or already categorized as suspicious. So we go to the next slide. We can walk through what we detected. So all the spots here where we have MNDR, that's where our platform was picking up traffic. And I'm going to talk through all these steps. And we see the one EDR detection across a few different hosts. So Rudy talked about this in the beginning. We kind of focus on the middle of the kill chain, the attack chain. So we do have detections for initial access and initial threat vector. In this case, what we detected with our rare domain newly seen in the environment was contacting out to a command and control server. And as our team dove into the details of what was that domain, what was that IP address, is there any available open source intelligence on it, it was quickly apparent that that was part of CACBOT and Squirrel Waffle campaigns that were active at the time. So we reported this immediately to our customer, and they were able to correlate the devices we identified for them with their EDR. And some of them had EDR detection for a malicious binary. But EDR, as we sort of covered, is not necessarily 100% coverage in your environment. Not every endpoint is going to support an EDR agent. New endpoints are stood up all the time, and unless you have really solid change control processes, maybe an EDR installation was missed. So not all of them were there. But they were able to correlate that this was an active compromise. As we began looking into the contact out to the command and control server, we wanted to take a step back and say, well, what started this activity in the first place? So we kind of backtracked to look at the activities that happened before, and we identified that that device had just checked email, visited live.com, and that was followed by a download. And we can look at these in the TLS activities. We're looking at things like data size. So the server sent X number of bytes, the clients that sent X number of bytes. By comparing these two items, we can, with high confidence, identify this was a download from that server. Even though the connection's encrypted, we don't know what the content was. It looks like there was a file downloaded. So right after that activity, that's when we see our contact out to command and control. As we dove in further, try to pivot around this infected device, we look for any other connections inside the network. So we're looking for lateral movement at this point. And we already talked about our platform is parsing out the SMB protocol. We have a lot of good, basically all of the fields coming out of SMB. So we were able to identify the user making an SMB connection, how it would authenticate it, source device, destination, what share path it was sending a file to, and what the file name was. In this case, the file names were just kind of random letters, .exe. And we could see that it was not a valid, essentially the username was blank in these activities. What we found was they were exploiting an old vulnerability, 2017, MS17010, Eternal Blue. In this case, it was Eternal Synergy. It was using a couple of different exploits from the same sort of family. But essentially what this did was create a null anonymous session on the target device. And by exploiting this particular vulnerability, setting that anonymous session to an admin session, giving it the ability to write binary and execute laterally. ultimately spreading to 47 compromised systems in this case. And so we're identifying all of this and providing this telemetry back to our customer as they're doing their incident response, helping them scope and ultimately contain and shut down the command and control communication. So by watching all of these things happen on the network, we identified 109 different attacker IP addresses, which your EDR platform's not going to do. We identified 5 command and control domains kind of fluctuating through all of this. But providing this all back to the customer relatively quickly, we were able to help them contain this within 24 hours since we detected.
I know from working with similar types of solutions, I wouldn't say competing products, but similar-ish service sets like MDRs. One of the challenges has been that it's alerting and picking up on traffic inside the network, which is great, but it is getting blocked or stopped egressing at a firewall, but that's not visible to the things that are monitoring inside the network. What are you guys doing about that?
Sure. So when we talk about activities in the platform, it's important to separate away the idea of packets. Gary talked about this a little bit. We're not necessarily interested in the packets themselves. So when we say we saw an activity contact a CNC server, command and control server, we're also seeing that response come back. So we're seeing that this is an active compromise and it's active communication with the threat actor infrastructure. Okay, so that was one example of detecting a compromise. And I think it's important to note on that one that having the network telemetry is ultimately what had the detection and what helps quickly scope and contain, but also having the EDR to correlate those devices was critical in solving that. I want to take a step back from maybe the more interesting compromise scenarios and talk about asset inventory. I think it doesn't get enough attention across industries, maybe because it's not as interesting, but it's critical for the next story we're going to talk about in a minute. But when a vulnerability is disclosed, how do you know what you're running on your system? Do we have that software installed on our system? Is our software affected by this vulnerability? Do we even have that server still running? Last year for SolarWinds, we had incident response come in. In this case, the environment had stood up. It was a throwaway server. It was a SolarWinds trial. They had never really even configured it, but they installed it. It was doing its auto updates. And because it was a supply chain attack, it got infected. Nobody was paying attention to that server. It was never meant to stay on for very long. It was just forgotten. I think NDR plays a key role here and can contribute to alleviating some of the pain around this challenge of asset inventory. The top 2 CIS critical controls have to do with this inventory of hardware assets and software assets. Just a couple quick examples. These are 2 different CVEs. The top one you see there, it might be a little bit hard to see, but that's a Java CVE. And I've highlighted one affected version is Java 8 update 121. The second one there is for Python 2x through 2716 for URL lib. So without NDR, you need to have a pretty solid software application inventory for your environment to know, am I running Python anywhere? Do any of our applications need it? Do any of our applications run Java? A lot of our endpoints might, depending on tools that we need to run, and Java is just a requirement. You might have some of this data that, EDR will report what applications you have running, and it'll, in this case, just tell you have Python 2.7 running or Java running. But in the Python example, it may not tell you what code's being run by Python. And so are we relying on this particular library URL lib? We'll look at the Java first. So you saw this kind of view in Gary's demonstration. We're looking at a query. In this case, we're just looking for all activities. From this case, the source device making an HTTP request where the user agent string has one value, a Java, curl, or Python somewhere in the user agent string. We get all our activities back from a period of time, and then we're summarizing the results. In this case, we do see that we have a device that's at least using this user agent, Java 1.8 update 121. At this point, we want to go investigate, this is vulnerable. What do we need to do to patch it? Can we decommission it? Was it authorized by our change control in the first place? We can start an investigation around that. Example here is the Python. So we get the same sort of thing. We see we do have Python 2.7 with the Python URL lib. In this case, there's quite a few activities, 64,000. And also in the results, we see some other maybe older versions that we should probably be taking a look at. Python URL lib 1.17. What is that doing? And so when we talk about asset inventories, because they're not that interesting and because it's a very challenging problem, we might do it maybe annually. We might do it for compliance assessment. We need to do PCI compliance every couple of years. So we get our inventory set that time. But within a week or 2 weeks, probably it's out of date due to all the change controls going on, especially as the environment grows. You have various DevOps teams, various engineering teams with their own IT stack, and just deploying all sorts of different software. It becomes very difficult to maintain that list. But if you have an NDR platform that's tracking these things, it's very quick to query, like, do I have anything that's using these user agents in this example? Okay, so for the next example, I want to talk about this asset inventory because this is a big deal, probably still is a big deal just because patching takes such a long time depending on the environment. But Log4j was a critical vulnerability first published in early December 2021. And essentially, Log4j is just a component of a web application server that handles logging, processes logs in some way. There's a vulnerability where you could send this special string at the bottom there. And that caused your server to call out to whatever IP address is listed there and execute whatever code is sent back. And it's important to consider how critical this was because in our typical web vulnerability scenario, we're not really thinking about logs and all the places and data that we're collecting. Most of the time I'm sending something in the URL that's going to trigger a vulnerability in the web server, maybe do a file inclusion. I might be sending something in cookies or in HTTP headers, as was in the shell shock vulnerability years ago. But if you think about a web app that's just logging everything, you could do a comment section on a website. You just drop this string in the comment section. At the time, you saw a lot of security researchers just putting this string in Twitter just to see what would happen. But as your application pulls those logs in, pulls the comment section in, processes this, it's potentially executing arbitrary code sent back from the attacker. We're going to go to the next slide. With our managed network protection and response service, we're watching these vulnerabilities publish. We're watching all of this kind of chatter, and we start doing proactive hunting against what we're seeing. So right away, we start looking at customer environments to kind of find out, first of all, does anyone have this? Are we seeing any active scanning? Are we seeing attempts to exploit? And then to follow on to that, are we seeing a response? Was the exploit successful? Did a call go out from the affected server out to potentially malicious infrastructure? And as we reported to our customers, the next day, I think, they reported back to us that we were the first to notify them. They didn't get the same quick response from their EDR platforms, because EDR platforms aren't necessarily going to flag on this. This is, at the time, this is a normal function of Log4j. So if you even have an agent on the server running it, it may not have picked it up. So slide is more of a case for having the managed service, right? So your enterprise gets this news that there's this critical vulnerability, and it's just a component of a lot of different software. It's not necessarily just a web server. Your security team needs to be focusing on identifying within their asset inventory, do we have the affected software? Both of these screenshots here are from the CISA guidance on how to determine whether you're vulnerable or not. And it's worth pointing out, this was not published at least a month or 2 months after the initial public disclosure. So there's a lot of lag time that the security team needs to be focusing on. How do we get patched? They don't really have the time to be sitting in front of their alert system and doing any retroactive hunts. You want to have that managed service that's doing that for you.
You are asking here, how quickly can an enterprise patch? How quickly can you detect? So how long is it normally taking from the first things that the engine sees until you really have a detection and this is flagged for the customers?
So it varies, but I'd say the activities that are searchable in the platform is under an hour. So we're doing analytics every hour. And so within that hour, we'll have new activities that we can be searching and hunting to identify these things.
At some point you were talking about the importance, or somebody was talking about the importance of EDR in this model. I'm assuming there's some type of integration for when these things are off network.
I'm not sure I understand when what's off network.
Well, so if they're not on campus and data is not going through the on-prem switches and they're remote and working from home or from Starbucks, what are we doing?
Yeah, that's a great point. So we're only going to have visibility in that case if they're coming through the corporate VPN and that's being inspected by one of our sensors. So if they're totally remote, not connected to the corporate network, we're not going to see that laptop connection. Thank you.
Could you possibly build a software-based sensor as well in the future?
Yeah, I think a software agent is possible. I don't know what the resource utilization would look like for something like that to do the analysis. But
I guess you haven't heard that question the first time, yeah?
Yeah. All right, so related to Log4j, these screenshots come from some work that our threat research team did in developing new models and alerts for this vulnerability. So I urge you to read that blog. But in the first screenshot, we'll just talk through what we're seeing. We do a query. In this case, we're looking for this string sent by anybody to a web app in either an HTTP header value or in the URI itself. Are they trying to just put it in the URI, have it logged in maybe the web access log to trigger the vulnerability? And we have one activity selected in that. And so on the right-hand side, you can see the activity details for the row that's selected. And you can see that in the user agent field, there is a domain that this server is meant to call back to if it can be exploited. And so right away, even if we don't do anything else, we can look and do some open source intelligence investigation on, is this a new domain? Does it already have reputation? Do we see any other detections for that domain? And so we can start pivoting on and triaging some of the scanning activity we're seeing. But we can take this a step further by chaining in our queries different types of activity that happen within a certain time window. So in this case, we're looking for the first hunt, which is our exploit string in an HTTP request. But we also want to follow that with, was there an LDAP request outbound right after? And in this case, that second screenshot shows you the result of that. Yes, we did get a hit. So the top activity is the one we have highlighted in the first screenshot. And then you can see the next row down is an LDAP request out to, not an internal IP making requests. So we did have an active, successful exploit. At this point, we want to be investigating that endpoint and doing what we can to remediate. And I'd like to point out the retro search here is an important point. So this was disclosed publicly beginning of December. That's not to say it wasn't exploited before then. So our platforms, depending on the deployment, are tracking 90 to 180 days of the activity metadata that you see in these screenshots. Once we have a public disclosure like this, we can go back and have we seen this pattern, even before, and identify compromise that way.
Is there any chance to throw more storage at it and make the retention time a bit longer?
So one of the features we have is full PCAP storage. And that I know that we can expand with additional storage. We can make sure we have full PCAP stored for a longer period of time. I don't know offhand if we can extend the metadata retention period.
Yeah, I'm just making an example. The SolarWinds case, everybody needed to look back at least 6 to 12 months into the data. And that is, I think, a very common use case.
Yeah, no, that's a great point.
I'm confused about the packet thing and the transit records. How much packets are you saving? How are you deciding when to save packets? How are you constructing the non-NetFlow records?
So how much we save depends on the deployment. In some cases, we're going to discard things that are completely encrypted. We're not going to store as much of that to make room for things that we can investigate. But for a period of time, depending on storage, we're saving everything. So depending on the environment, again, and how many activities we're seeing, that could be 24 hours of full PCAP, or it could be a week of full PCAP. It depends on the deployment.
So you're saving the full PCAP, and then you're analyzing the full packets and creating some kind of database for yourself to refer to longer term, and then dropping off the original packets as you run out of storage?
Yeah, that's right. So as the data comes in, it's analyzed, and all of our metadata is added to those queryable databases that we've been looking at in these screenshots. The PCAP is then stored for longer term storage for a security analyst to come in if we need to investigate in the full PCAP.
Okay, so I'm just sorry, I'm being a little dense here. I'm trying to wrap my head around how the bloody thing works. So your agent on the switch is essentially an agent that's internally tapping all of the traffic, sending it over to the server that's doing this. We're storing these full PCAPs on the server, parsing through them and generating your metadata that you're saving long term. And as you run out of space on the server, you throw off the oldest packets.
I think that's accurate. I think the important distinction, though, is that the parsing is occurring on the switch, as Gary was talking about earlier. So the parsing and that metadata extraction happens at the switch level and is forwarded to a nucleus that's doing the analysis on the back end.
So how do you decide what packets to send over for longer term saving?
All of the PCAP is stored depending on storage availability.
Okay, all of the PCAPs are stored, but you're offloading the processing of the metadata to the switch, which is busy forwarding the packets.
Yep, I believe that's correct, yes.
Yeah, that's actually confusing, right? Because if you're going to offload the whole PCAP to a server anyway, then why do any analysis on the switch?
Yeah, thank you. I was wondering why I was so stupid.
Yeah.
Like doubling back, almost in essence.
Right. Now, you're taxing the heck out of that switch now, because you're not only doing a full span to drive the packets to another place, but you're also processing the packets and then spitting off metadata.
And that's probably going to weigh it down.
Streaming the data you just created in addition to the packets.
Right.
Right. Double the workload, and it's going to weigh it down.
We might be mixing up a couple things here. There's the switch sensor, which it does the parsing and forwards those parsed records to the what we call an analytics hub or nucleus. So that's one option for deployment, one architecture. There's a totally separate one, which is what we could probably think of as traditional, where switches are not part of the analytics pipeline in any way, and you are from a totally standard switch or router mirroring or tapping traffic from a core, usually somewhere at the edge or major demarcation point between geographic locations. You're just taking all the traffic going over that pipe, creating a copy of it, and that goes to a standard sensor. And the sensor records all the traffic, in this case, records all the PCAP, also parses. So, this is the thing about the switch that's really interesting is now the switch can do what the sensor is doing minus recording the PCAP, right? In the traditional deployment model, all that PCAP is recorded on one sensor. Hardware-wise, it looks like a server, big, lots of storage. And then that sensor, like I said, parses all the traffic, forwards the parsed information onto the nucleus or analytics hub. And that's where it's the same. So you're either doing the parsing on that traditional sensor or you're doing the parsing on the switch. If you have the traditional sensor, you're going to have massive disks and you're going to be able to record, traffic for, depending on the environment, anywhere from, several days to several weeks,
Okay. And so
that is the difference between having an Arista switch and having a random third-party switch, yeah? But you can combine on searches both log sources, yeah? Do I get it right?
The Arista switch can do the job that we've only historically ever seen network analytics sensors do. Yes.
And you've got
but the analytics engine. So I have some data centers with Arista and some with third party. But at the end of the day, the analytics engine could give me an heuristic view about both data sources.
The analytics engine needs the information coming to it to be in a format that it understands. So it either needs to come from the traditional sensor that you can pair up with it. You know, you can buy it all in one too. You could buy a sensor and analytics engine in a single device, or those can be broken apart into two separate. They're 2U type devices, right? You can separate that so that you can create a tiered architecture, or an Arista switch, which can now fill the role of a traditional sensor, right? And the big advantage there, the massive advantage there is you have the switches deployed anyways, all over the core of the network. The challenge that we've had historically, starting with IDS, then going into IPS, then into NTA, and now NDR, the challenge that the entire industry, the network analytics industry has had is getting visibility into the core of the network. You can't tap all that traffic and send it off to these sensors, and you can't deploy sensors all over these, edge cores and stuff like that. And so now that problem's been solved because you have switches there anyways, and now those switches can do the parsing and send the recorded traffic back, or the parsed records back. Is that clear as mud?
I think we've gotten there, right? So I think that what it is if you've got the new Arista switches with this capability to do on-device processing, then you can do on-device processing and you just send the metadata back to the system. And if you don't, if you're in a brownfield deployment, which a lot of us end up in most of the time, you can send PCAP data from any switch through the sensor and then get the same data visibility.
100%. Yes. Okay. Yep. Got it. Metadata, keyword.
So with so much traffic being encrypted these days, how are you seeing inside of it to be able to tell what is actually going on?
That's a great question. So we do a lot of TLS characteristic analysis where we'll have, TLS requested server name will be available in the packet. We'll have the TLS cipher suite that was selected. Using things like that, we can do a lot of profiling about applications in use and doing some application detection that way.
If you want more follow-up information on that, you can do a search for Awake Security encrypted traffic analytics, rethinking your approach to encrypted traffic analytics, something to that effect. You should find it quickly. We have some YouTube videos and presentations. I think also presentations that were given at SANS. But there's a relatively standard approach to TLS fingerprinting. So you can actually look at the TLS packets and in many cases tell exactly what application generated that traffic, not just the device type, but the specific application that generated that. But we've taken it a lot farther, and there's a lot more information in those reference presentations if you're interested in the subject.